My dear students, now we are going to look at mod-11 asynchronous counter. We know how to design the counters, of course, asynchronous counters. But so far what we have seen is we have seen with respect to T flip-flop and J flip-flop. Now we are going to look at D flip-flop. So what we try to do is we will look for how many D flip-flops required in order to carry out this design. What is the problem given? The problem given is mod-11 asynchronous flip. What is mod-11? The one which counts from 0 to 1, 1 to 2, 2 to 3, 3 to 4, then 4 to 5, 5 to 6, then to 7, then 8, then 9, then goes back to 0 is mod 10. But what we want is mod 11. So I need to extend to one more step. So what is that is, we'll go for one more state called mod 10. From there it will go to total number of states are 11. So what should not be there in this count sequence is whenever it becomes 11, we should get reset. It should be 0. How many zeros? 4 zeros. How can I say? What is the value of n here? N is equals to 11. In general, whether it is synchronous or asynchronous, number of flip-flops required is 2 power n should be greater than or equals to n. The given value of n is mod n is equal to capital N is 11. Where small is number of flip-flops. Small n is number of flip-flops required, right? So now what we try to do is, when n is 11, so 2 power n should be greater than or equals to 11. Let's say n is equals to 3. It is 2 power 3 greater than or equals to 11 is false. So let's make n is equals to 4. When n is equals to 4, 2 power 4 is greater than or equals to 11. 16 greater than or equals to 11 valid. N is equals to 4. Number of flip-flops required is number of flip-flops required is equals to 4. In the step 2, what we are trying to do is, let's use D flip-flop. Okay. So next what we can do is state diagram. State diagram is well known. I have shown you just now. Okay. You can draw the state diagram. We are aware of. Okay. So it will start from state 0. It will go up to state 10. So state 0, state 1, state 2. Okay. 0 0 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 dash 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 up to what exactly? Last value is 1 0 1 0. Then it will go to 0 0 0 0. This is state diagram which we know, right? Now wherever the dash is there, that you need to fill it up. That you are aware of. Okay, you are well known. So now the question is there any truth table? Is there any reset logic? So we will look at truth table. What is truth table? What is the clock input? Clock input and output. What is output? Output is state. So for clock 1, output is 0 0 0 0 0 4 zeros. Clock 2, output is 0 0 0 1. For clock 3, output is 0 0. What exactly? 0 0 1 0. So on and so forth, right? So will be gone. Now what we try to do is, for this we need to write the full truth table. So I will show the truth because there is no space. I will show in the next page the full truth table. I write clock input, then flip-flop states, that is output. So state of flip-flops, So state of flip-flops are, let's say, 4 flip-flops: QA, QB, QC. Clock input is CLK, is the input. So let me write clearly clock input as clearly. Okay, this is clock. When clock is equals to 1, output is 0 0 0 0. So what about the clear logic? There should be output reset logic. Output output reset logic. What is this logic for? To make the counting sequence in between half. So when clock input is 2, this is 0 0 0 1. When third clock is applied, 0 0 1 0. Fourth clock applied, 0 1 0 0. Fifth clock applied, 0 1 0 1. Sixth clock applied, 0 1 1 0. Seventh clock applied, 0 1 1 1. Okay. For all these things, what is the reset? Should we do the reset? No, we don't require. We are not supposed to do reset. So what is the clear value? Clear value should be 1, 1, 1, 1, 1, 1, and 1. For 8th clock pulse, 1 0 0 0 0. Still we are not trying to reset. For 9, 1 0 0 1. Still it is 1. For 10, it is 1 0 1 0. Still it is 1. For 11, for what is 11? 1 0 1 1. Which, okay. What is the meaning of this is we are clearing the flip flop. Clear flip flop. When it is 1 0 1 1 11. That means what is happening? You are starting from 1 and you are moving through up to 1 0 1 0. Then from 1 0 1 0 you are going to 0 0 0. So it is cycle stop. That means it comes like this. How it will be? So it will come like this coming down. Then it will start with 0 and once again will come down. Once this is done, it will go to the back, then it will repeat. So this is how the mod 11 counter is going to work. This is what exactly truth table. From this what we can see. What about the rest of the cases? What about the rest of the cases? Rest of the cases like 12, 13, 14, 15 and 16. I can define for all the rest of the cases my output should be 0. So what is the meaning of that is if anything other than 0 to 10, if at all if it is there in the register and if you give the clock, okay, by default it clears. For 1011, for 1100 up to 111, what we are trying to do is, okay, we are making like 1101, okay, 1110, then 11. For all these cases, what we are trying to do is we are making output equal to 0. So what is this that we are trying to do is, if you look at this, we can get an expression for the logic. What is that is, okay, what I try to do is, by looking at the above table, I write the output reset logic. So output reset logic, if at all you see, this is 4 inputs. So from where we are going to get output reset logic? From the inputs QA, QB, QC, QD. So I will take 4 input K map. In that, from QA, QB, QC, QD, 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1 0. So it is 0 from 11 to 15. So numbering we know 0, 1, 3, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 14. So from 11 onwards, it is from 11 it is 0, then for 12 it is 0, for 13 it is 0, for 14 it is 0 and 15 it is 0. For rest of the cases it is. So what are the rest of the cases? For 0, 1, 2, 3, 4, 5, 6, 7, okay. Then 8, 9, 10. So what I can do? I can take this 8 ones into one combination. Okay. So what I can do is further I can take this two, I can combine with this two. Okay. Then I can combine these four ones. What are the four ones possible? This one, this one, this one, and this one. Right? So what is the expression that I'm going to get? The expression for this is nothing but what is this expression? Clear logic or reset logic. So let us call clear logic as clear logic, whatever is there, that clear signal should be what exactly this clear should be. So clear should be, this is what exactly 8 ones. 8 ones combination is how much? This 4 has gone, so it is QD bar, QD bar plus what is expression for this? What is expression for this? Let's look at it. Expression for this, what is there common is here QA bar, from here QC bar. So it is QA bar, QC bar. Now for this from there QB bar, QC bar, QB bar, QC bar. Okay. So from this what I can say is the overall expression for clear is QD bar, QC bar, QA bar plus QB bar plus QC bar. Okay. So what is the difference between this and the rest of the designs is we will look into it. Okay. So if I make this, then it will be done. Okay. So what I do is now I will draw the circuit. Now for this, if you look at the logic, we have 4 flip-flops. Okay. 4 flip-flops. Done. So what I need to do is I will take one thing is that there is a QD bar I need to take. Then what I need to do? QC bar, QA bar. You take QC bar, QA bar and give it to AND gate. Then you take one more input, QB bar and QC bar. QA bar, QC bar, QB bar, then QC bar. You take them, give it to AND gate. All these three, give it to OR gate. We will get an output. This where we are connecting is, we are connecting this to, okay, clear input of this. Okay. So what is going to happen is, when this is being done, what exactly this is going to happen is, this is not only makes output is equal to 0, okay, only not only for 1011, anything greater than 1011, I will make the output is equal to 0. Okay. So now this is your flip-flop. This output is given to the input of the next flip-flop. Output of this is given to the next flip-flop. Output is given to the next. Let's say this is A, this is B, this is C, and this is D. And this is your TA, which is 1, TB, which is 1, generally. Oh, if we are using T flip-flop, but what we are using? We are not using flip-flop, T flip-flop. So we will make small change. What we are using is D flip-flop, right? We have made that determination already. So I will make that D as T. So to do that, how do you use the D as T? It's very simple, right? So what we can do is, I will take one exclusive OR gate. I'll give it to the input. I'll take this, okay, Q bar of this same flip-flop. I'll connect it over here. Here it is T input. That input is made as, this is TA. Similarly, I'll take one XOR gate. Output of this I'll going to give it to you. One of the input is TB, which I'll make it as 1. The another input that's supposed to come is from Q bar. This is Q, this is Q bar. Q bar is connected to the input through exclusive OR gate. this is TC, generally we will connect it to 1. Okay. Similarly, this is Q, this is Q bar, this is connected to the XOR gate, connected to the input, to the feedback. Another input to that is we have is TD, which is our generally. So in this flip-flop, what we did is, this is also asynchronous counter, which counts from 0 to 10. Okay, once it reaches 11 or anything greater than 11, this circuit will make the output is equal to 0. It will make output is equal to 0. In that way we have decided. That's the reason why this is circuit. If you want to make the output to be 0 only for 11, so in that case what is exact is 1011, this is QA, QB, QC. So what I need to do? I'll take some NAND gate. Okay. If I connect this to QA, then QB, then QD, QA, QB, QD from this, because this is QA, QB, QC, then QD, right? So QD is 1, QA, QB are 1. So QA connected, QB connected, QD connected. This will connect it like this. Okay. What is the difference between this and that is very simple. If you connect this one, if at all you make this arrangement, okay, it will look for 1011. Whenever it becomes 1011, it will make the output is equal to 00. Once output is 00, it will follow the sequence. Then next is 0001, okay, 0010, so on. But what we are doing in this case is, we are not only looking for 11 or anything greater than 11, we don't want. We want for all those cases, anything greater than 11 and 11, my output to be 0. For that, this is the circuit. So either you can do this way or you can do this way. So in the truth table, what I have developed is, I developed a truth table where I need a clock, I need a reset logic. I'm sorry, it is not clock. I need a reset logic, okay, such that anything greater than 11 or 11, output should be made 0. So for that, this technique I have seen, I have shown you already. This technique I have shown you. Okay. With this, there is more than one solution in it. So for all unused states, what we are trying to do is, we are initializing it to 0. Any unused state. What are unused states? 11, 12, 13, 14, 15. All unused states. What are used states? 0 to 10 are used states. For all unused states too, we are going to a used state. That means your circuit will not be struck with any unused case. Let's say for in this register, by due to some error or noise, if it is loaded with 1100, what is the next state? Next state is not defined if I solve it like this. But what we did is, now anything unused state is there. From unused state to used state it will come. Once it comes to used state, we have a predefined way how to move in used state. If it is at 00000, okay, then we'll go to the next 00001, then 2, 3, 4 up to 10. So this is how what we are trying to do is, we are avoiding the counter strucking with unused state. There is a possibility that if we are loading with 1100, okay, it may struck with 1100. It may not move here and there. Possible. Okay. So in order to avoid such strucking with certain code pattern, what we try to do is, we try to define, okay, for all unused states, okay, for all unused states, there is a next state as a used state, which is 0 in this case, which works. Okay. So on the whole, this is one solution. This is another solution. This solution have no issues, whereas this solution has a issue. What is that issue is? For this solution, what is the issue is? Okay, for any unused state, your counter may struck up. It may get stuck. Okay, may.